And we're back with yet another derivative and yet another day where I admit that I've been lying to you by omission. Today we learn to take the derivatives of implicitly defined functions. So the first thing we have to talk about is what the heck it means to be implicitly defined, and then how to do it, but also you might want to talk about why this, I don't know, third grader is even thinking about it. But I'll tell you one thing he knows. He's not going to use the chain rule. Okay. So you might want to take a look at this function. This is the kind of function we're going to be talking about in this section. And notice that it doesn't look like the other functions we've been looking at, does it? It does not. Okay, so far, every derivative I have thrown at you has been the derivative of an explicitly defined function. Explicit meaning that we have y in terms of x. So aside from the parametric stuff, which is a whole other world, when we give you an equation that has y and x, so far it's been y in terms of x. So like y equals whatever, or f of x equals whatever. And we've learned how to take derivatives. So we still have all those derivative rules in our pockets, right? We still have the product rule and the chain rule, and the quotient rule, and sums and differences, and e to the x, and all that stuff. But when we are looking at functions that are defined implicitly, we have to kind of add one more layer and a little bit of algebra to the mix. I'm not going to lie to you. Historically, the algebra is the challenge of this section. So brace yourself for that. Most people understand the calculus and then they get lost in the algebra. But I do have kind of a method for getting through the algebra because it turns out to be just about the same every time. So what we're talking about here when we talk about implicit functions are functions where the x's and y's are all jumbled up. Okay, now sometimes if the x's and y's are all jumbled up in an equation, you can say, okay, that's nice, but I'll just solve for y, right? Sometimes you can take an equation that has the x's and y's all jumbled up and do some algebra to it and rewrite it as a y equals. But that's not always the case. Look at this equation right here. You have a y squared here, and you also have a y inside your sign. You don't have a prayer of solving this algebraically for y. If you try to isolate the y here, you're still going to have this y inside the sign. And the only way to get the y out of this is to take the inverse sign, or the arc sign of both sides, in which case you have now encased this inside of an arc sign. So the only way to get at this equation will be by using the technique I'm going to show you today, by using implicit differentiation. Implicit differentiation is, again, the kind of the strategy that we use when our variables are jumbled up, our x and y's are jumbled up. Kind of you've been using it since day one, but you didn't know you were using it. It's just like when you didn't know you were using the chain rule because all your chains were times 1. This is the next layer of that. You've actually been doing implicit differentiation. It's just that all of the things that you should have been doing were just times 1s, and so it didn't matter. And the good news about implicit differentiation is if you're not sure whether you should do it or not, you can always just do it. It can't hurt. You'll still get the right answer if you do implicit differentiation where it wasn't necessary. But if it is necessary and you don't do it, then you will not get the right answer. So when in doubt, you can go ahead and use this method. It's kind of a fallback there. So let me go through the actual method so that you can see what we're talking about here. All right, so I want to know the slope of this circle graph. Now, if you look at this graph, you may notice, without even looking at the equation, that the slope is going to depend not just on x, but also on y. So for example, if I say to you, find the slope of this graph when x equals 3. Okay, well, if I put a line at 3, you're going to notice that line hits twice. It hits once here, and it hits once here. So if I ask you to find me the slope at x equals 3, you better have a follow-up question, right? So do you want the slope here, which is negative, or do you want the slope here, which is positive? There's 2. And that's the case for just about every x value other than 5 and negative 5. So for every x value here, there's actually going to be 2 tangent lines. One of them is going to be positive, and one of them is going to be negative. So, in other words, the slope of this function doesn't just depend on x. It depends on both x and y. So in order to evaluate the slope, I can't just have an x value. I have to have an x and a y value. And that happens a lot with implicit differentiation. Sorry. Okay. So here's what we're going to do for implicit differentiation. Again, we're going to use the same derivative rules that we've always used, the same rules that we've always known. If there's a product in front of you, do a product rule. If you're looking at a quotient, do a quotient rule. If there's a chain rule involved, do it. There's just one extra kind of layer. So what we are going to do is we are going to go whole hog on this idea that you can do anything you want to an equation as long as you do it to both sides. Right? I can add 5, I can subtract 10, I can square both sides, I can take the square root of both sides. That's the rule, right? That's the big algebra rule. Well, it's not just an algebra rule, it's a math rule. You can do anything you want as long as you do it to both sides. So in calculus, we're like, okay, well, I'm going to take the derivative of both sides. And again, you've been doing that. When I give you y equals x cubed and ask you to take the derivative, dy dx isn't just notation. It means the derivative of y. Right? Or y prime. You took the derivative of y. What you didn't write is that the derivative of y is also equal to 1. Right? So again, this is kind of a, I've been lying to you a little bit. Notice in the last section we noted that dy dx is more than notation, and that's the case here as well. Dy dx is a lot more than just notation. So what we are going to do is we're going to take the derivative of both sides with respect to x. And this is an incredibly important phrase right here. We're taking the derivative with respect to x, and that's important. What's going to happen when we do that is we're going to see dy dx's or y primes pop out in our equation as we do that, like it did up here. The only difference is with implicit, those dy dx's are going to be kind of spotted through the equation. And then we're going to have to algebraically solve for it. So we're going to treat dy dx like it's its own variable, because it is. Dy dx is a quantity that means the slope of the function, the change in y over the change in x. And then once we solve for that, we'll have an expression. Maybe it'll just depend on x. Maybe it'll just depend on y. Maybe it will depend on both x and y. We're going to find out. Okay, but before we look at that circle equation again, I just want to stress this one more time, the way I've been lying to you. Okay. If I ask you to take the derivative of x cubed with respect to x, you say 3x squared, and that's all we write. Okay. What we have not been noting is that we took the derivative of this with respect to x. Right? So what we're going to have to do for implicit differentiation is we're going to have to add a little something here. A chain rule piece, if you will, that says, by the way, that derivative I just took, it was a derivative of x with respect to x. On the other side, normally you would have just written dy dx. But what we're really writing is, oh, the derivative of y, that's 1. The derivative of y is 1. It's just like the derivative of x is 1. Both don't change depending on which side of the equation you're on. But then we say, well, also, by the way, that derivative I just took, it was a derivative of a y with respect to x. And the way that looks is this. So the derivative of y is 1, just like the derivative of x is 1. And then this piece is the implicit piece, where we say I took the derivative of a y function with respect to x. Now again, we've just been writing this part and acting like it's just notation for the derivative. Now, over here, we took a derivative of an x thing with respect to x. So what we need to write here is a d, of course my picture is in the way, is a dx dx. In other words, Over here, I took the derivative of y with respect to x, so I'm going to do dy dx. On this side, I took the derivative of x with respect to x, so I'm going to do dx dx. That's the implicit piece. Now look, here's the thing. Like I said, you've been doing this all along. Every time you had a function that was y in terms of x, everything, when you took the derivative on this side, this derivative was always 1, so why write it? We didn't. And over here, since it was y in terms of x, everything on this side was an x term, which means everything on this side was a derivative of x in terms of x, and all this is a 1. So again, why write it? So you've been doing this all along. You just didn't know it. Because you weren't writing this one and you weren't writing this, because that's just a fancy form of 1. But when it comes to implicit, we have to write it. Okay, so let me show you what I mean in this beautiful example with a circle. All right, so let's take the derivative of x squared plus y squared equals 25. Now, I could solve this for y and make two functions, right? The positive root of 25 minus x squared and the negative root of 25 minus x squared. I'm not going to do that. I don't need to. I have implicit differentiation in my pocket. All right, so let's take the derivative of this. The first thing I need to do is take the derivative. I'm going to use my sum and difference rule, right? I have 3 terms here. I'm going to take their derivatives individually. This is a sum or difference. So I'm going to take the derivative of x squared with respect to x. I'm going to take the derivative of y squared with respect to x, and I'm going to take the derivative of 25 with respect to x. Woo! All right, so the derivative of x squared with respect to x is going to be normal old boring 2x. The layer we're adding for implicit is that since I took the derivative of an x term with respect to x, I'm going to tack on, I took the derivative of x with respect to x. Then I'm going to take the derivative of my y term with respect to x. So here it goes. Derivative of y squared is 2y. And I note that I took the derivative of a y thing with respect to x. Then I'm going to take the derivative of 25 with respect to x. Okay, well, the derivative of 25 is 0. So if you want to think of it as a 25x to the 0, then you could write dx dx here. If you want to think of it as a 25y to the 0, you could write dy dx here. In the end, it doesn't matter. There was no variable on it, right? And it doesn't matter what you write here because 0 is 0 is 0. So this whole thing is going to be 0 anyway. But look what happens on the other side. Dx dx is just 1. Dy dx, that's what we're after. That's the slope. So all I have to do here is algebraically solve for dy dx. Now if that looks ugly to you, you are free to replace dy dx with something else like a star or something. I had a kid a couple years ago that used to put a circle around it and write world peace, and he said he was solving for world peace. Oh, that's such a nice idea. But if this is bothering you, if this looks ugly to you, you can always replace dy dx with some other symbol or variable and then solve for it. Just make sure in the end you write dy dx equals. But we're just going to algebraically solve for this guy. So I'm going to take the 2x to the other side. And then I'm going to divide both sides by 2y. So I'm going to end up with dy dx equals negative 2x over 2y. The 2's cancel. And you get negative x over y. So again, I'm using my same rule. Derivative of x squared is 2x. It's always been that way. The derivative of y squared is 2y. The derivative of 25 is 0. The only thing we're adding here, it's almost like an extension of the chain rule, is that you're tacking on to each term. Every time you take a derivative, you are tacking on, I took the derivative of x with respect to x, or I took the derivative of y with respect to x. Your dx dx's are all going to be 1. Your dy dx's, you're going to solve for. So some people say, well, do I have to write the dx? And the answer is no, you don't. Right? Now, I am going to write it because I want you to understand that there's nothing special about taking the derivative of the y terms versus the x terms. I'm not doing dy dx exclusively for y. We're doing the same thing when we take the derivative of an x term. It's just that the thing we tack on is 1, so some people don't like to write it. The other question that people ask me is if they have to use dy dx, they say, can I use y prime? Absolutely you can. I don't, for 2 reasons. The first is dy dx gives me more information. It tells me, it reminds me what I'm doing. Right? If I write dy dx, I took the derivative of y with respect to x, versus when I do the derivative of x, I write dx, and I look at that and I visually say, oh, that's a 1. Goodbye. The other reason I do not write y prime is because y prime starts looking a heck of a lot like y to the first. And then I get a line into my algebra, or 2 lines into my algebra, and I go, Brayden, you're so dumb. Why'd you write y to the first? Who writes that? And I treat it as a y to the first, and I stop writing y prime. And then at one point I go like, where'd my derivative go? I lost my derivative. So it's easier to lose for me when I write y prime. Some people really prefer to write y prime. Ms. Casciato writes y prime, makes her happy. If you can keep track of it, do your thing. I never write it. I always write dy dx. And I will continue to write dx as well. If you're comfortable not writing it, when you get to a space where you're not comfortable writing it, if you do, that's fine. You don't need to write it. It is just equal to 1. Okay. So we're going to talk about this derivative. I want to look at the graph here. So check out the derivative here. Here's my derivative, negative x over y. So notice, when x is 0, look what kind of tangent lines you have. Horizontal ones. Oh no. When y is 0, look what you have. Vertical tangents. If x and y are both positive, so up here in the first quadrant, you have all negative slopes. And in fact, that slope at 3, we can get it now, it would be negative 3/4. When x and y are both negative, look again, negative slopes. It's only in your second and fourth quadrants where one is positive and one is negative that cancels with that guy and we end up with positive slopes. But again, notice the symmetry here on the graph of a circle, right? That the magnitude, oh my goodness, the magnitude of your slope at 3, 4 is going to be the same as the magnitude of your slope at negative 3, 4, negative 3, negative 4, and 3, negative 4. Right? These are all going to be either positive or negative 3/4. So it's kind of neat the way this kind of just fleshes that out for you. Okay. All right, so my floating head is all over the place in this video. All right, so when we take a look at this graph, by the way, if you go online and you type graph implicitly defined functions, you can find some pretty cool implicit graphers because your calculator won't graph implicitly defined functions. When you go into y equals, it's exactly that. It's y equals. You can't give your calculator an implicitly defined function, but you can go on the internet and do it. And it comes up pretty cool. Okay, so for this one, could I solve it for y and have positive root x, negative root x? Sure. Why would I when I could use implicit differentiation? Please. Okay, so look, we can look at this and know, look, if I give you an x value and I say give me the slope when x equals 5, there's one here and there's one here. So obviously my slope isn't just dependent on x. So we got something going on here. All right, let's do our derivative. So I'm going to take the derivative on this side with respect to x and take the derivative of each term with respect to x. Okay. The derivative of y squared with respect to x. Again, the derivative of y squared never changes. It's 2y. I can just find my pen. Everybody would be so happy. 2y. Okay. Then we say, oh, what'd you take the derivative of? I took the derivative of a y term with respect to x. That's going to be important. Over here, I'm going to take the derivative of x, which is 1, and it was with respect to x. So I took the derivative of an x thing with respect to x, dx, dx. So simplifying down, this is just a 1. Who cares? I end up with 2y dy dx equals 1. In other words, dy dx, my slope, is equal to 1 over 2y. In this particular equation, slope doesn't depend on x at all. All you need to define slope is a y value. So look, the exact opposite of a y equals x squared, right? A regular parabola. If I give you a y value of 1, there's only one point on this graph that goes with a y value of 1. So if y is 1, I have a slope of 1/2. If y is 2, here, or no, wait, that's not when y is 2. When y is 2, I'm over here, right? When y is 2, I have a slope of 1/4. Okay. Notice when my y values become negative, I get negative slopes, and this equation is going to flush that out for me. If y is -1, my slope is -1/2. That's the worst tangent line anybody ever drew. If y is -2, I'm going to have a slope of -1/4. But when you take the derivative implicitly, that's all going to flush out for you. You don't have to be able to look at the graph and go, oh, my slope's going to depend on y, or my slope's going to depend on x, or it's going to depend on both. Very nice. I like implicit differentiation. All right. How about this graph? Love it. Okay, so let's do this. We are going to take the derivative of each term individually and tack on our d dx, whatever it may be. Maybe it's a dx dx, maybe it's a y dx. Doesn't matter to us. All right, so I'm going to take the derivative with respect to x of 2y. I'm going to take the derivative with respect to x of x squared. And I'm going to take the derivative with respect to x of sine y. One at a time. So, derivative of 2y is going to be 2. It was a y term, so dy dx. The derivative of x squared is 2x. It was an x term, so dx dx. Finally, the derivative of the sine y is the cosine of y. It was a y term, so dy dx. This is the first one that we're seeing where the algebra gets a little stickier. Okay. So notice again, we have a dx dx in here. This is just a 1, so who cares? Notice I have a dy dx here and dy dx here. I need to solve for that. So look. Same method every time. I don't care how many dy dx's you have. Your strategy is this. Get everything that has a dy dx term to one side. I like to move it to the left. And everything that doesn't to the other side. I like to move it to the right. So what I'm going to do is I'm going to leave this 2x here. I'm going to move this cosine y dy dx over here to be with the 2 dy dx. So I'm going to have 2 dy dx minus cosine y dy dx equals 2x. Now why would I do that? The reason I'm doing that is because now I can factor this dy dx out. That's what I want. I want to solve for it. So I'm going to factor it out. Dy dx equals 2 minus cosine of y. And that's still all equal to 2x. So once I've factored out my dy dx, I've got one thing left to do to finish this thing off every time, and that's just divide by that quantity. So I'm going to have that dy dx equals 2x divided by all this stuff. So 2 minus cosine y. And again, you might have 5 or 6 dy dx's. That's fine. Get all the terms that have dy dx over to the left, factor it out, and then you're going to have a quantity, divide by it. That's going to isolate your dy dx every time. Okay? So it might look messy algebraically, but you're following the same steps every time. So again, notice here my slope is not going to just depend on x. It's going to depend on y as well. All right. These are so fun, in my opinion. Okay. Let's do one more, and then I'll let you digest this a little bit. Okay, I have 2x cubed, 3y squared, and 8. So let's take their derivatives individually. The derivative of 2x cubed is 6x squared. I took the derivative of an x term, so it's dx dx. Minus the derivative of 3y squared is 6y. I took the derivative of a y term, so dy dx. And then that equals derivative of 8, which is just 0. And again, it's not that this is special and we don't need to write dx dx or dy dx. And don't get hung up on the fact that it doesn't have a variable and I don't know which one to write. It doesn't matter. It doesn't matter. This is 0. I don't care what you write here. dx dx, fine. It's still 0. Doesn't matter which variable. Okay, so this is 1. That's 0. So I'm left with 6x squared minus 6y dy dx equals 0. So if I want to solve for my dy dx, I've got negative 6y dy dx, negative 6x squared. So my dy dx is going to equal negative 6x squared divided by negative 6y, or x squared over y. Again, we've got a slope that depends on both x and y. Pretty fun, right? Okay. Now, this is what I'm showing you here are really basic implicit differentiations. The next time we chat, we're going to talk about stuff like this. So notice here, I have my x's and y's jumbled. They're inside of a cosine, and notice they're in a product. So it gets a little more, it's a little stickier. No new rules, but just a little stickier, kind of keeping track of what you're doing when you start having x's and y's jumbled together as products in chain rules and stuff like that. So we'll look at those next time we're together. For now, I just want you to practice the most basic of implicits. Okay? See you next time.